In calculus, we see limit a lot. Do you know what a limit is? Let's do a problem together. Use the epsilon-delta definition to prove the following limits.
Wait, what? What is epsilon-delta definition?
Well, here's the epsilon-delta definition from the textbook. You should pause the video and read it. Let me also try to explain the epsilon-delta definition. As an example, let's look at the limit of f of x as x goes to 2 equals to 4. The informal definition would say this means as x getting closer and closer to 2, f of x is getting closer and closer to 4. For me, I always picture this as a sequence of points representing x getting closer and closer to 2 as its corresponding sequence of points representing f of x getting closer and closer to 4. Now, what's the epsilon-delta definition, which is supposed to be the formal definition of limit? Here we go. For any positive epsilon, there exists a positive delta such that absolute value of x minus 2 less than delta implies absolute value of f of x minus 4 is less than epsilon. Well, this is the epsilon-delta definition of a limit. It is a logically correct sentence, but no human beings talks like that, maybe except the mathematicians. My suggestion is you should first try to understand the logic behind this sentence of epsilon-delta definition, and then you practice saying it again and again. Eventually, it is totally okay that you can just say this definition out loud without even thinking about the meaning behind it. If you want to add some emotion into the definition of epsilon-delta, you can say something like, you tell me how close you want f of x to be close to 4, and I will ask my x to be this close to 2 to fulfill you. Now that we have this formal, precise epsilon-delta definition of limit, when we want to prove something like limit of f of x as x goes to 2 is equal to 4, all we need to do is to prove the existence of delta. Now we are ready to use the epsilon-delta definition to prove the following limits. Before I prove these limits, I'd like to comment that epsilon-delta definition is more used in proving general theorems involving limits. Rarely it is used for proving the limit of a specific function. The point of exercises in this video is to demonstrate the epsilon-delta definition of limit. Let's first prove the limit of x squared as x goes to 2 is 4. Well, the precise definition of this is for any epsilon greater than 0, there exists delta greater than 0 such that the absolute value of x minus 2 less than delta implies absolute value of x squared minus 4 is less than epsilon. The thing we are really proving is the existence of delta. Or in another word, for any epsilon greater than 0, find the delta that satisfies the following condition. In order to find delta, let's start with x squared minus 4 less than epsilon. That is, x squared wants to be close to 4. How can you make that happen? We split x squared minus 4 as x minus 2 times x plus 2. Our goal is to find how close to 2 x needs to be in order for x squared close to 4. Now the question is how close to 2 x needs to be in order for x minus 2 times x plus 2 small. Intuitively, when x is close to 2, x minus 2 is close to 0, and x plus 2 is around 4, so something close to 0 times something close to 4 should be close to 0, but we need to quantify everything. If x is close to 2, say the distance between x and 2 is less than 1, then x should be between 1 and 3, and x plus 2 should be between 2 and 5. The absolute value of x plus 2 should also be between 2 and 5. Eventually, the only thing we can ask for is absolute value of x minus 2 less than delta. But we already know if x minus 2 absolute value less than 1, then we have x plus 2 absolute value is between 2 and 5. Which is good. So to quantify how close to 2 we want x to be, we will first ask absolute value of x minus 2 to be less than 1, because it gives us a precise control of the absolute value of x plus 2 can be. Since x plus 2 absolute value is less than 5, we will also ask for x minus 2 absolute value times 5 is less than epsilon. We replaced the absolute value of x plus 2 by a number because eventually we only want to see expressions involving absolute value of x minus 2 and how small it needs to be. Let's do a quick check that the absolute value of x minus 2 less than 1 and absolute value of x minus 2 times 5 less than epsilon does imply absolute value of x minus 2 times x plus 2 is less than epsilon. Okay, if x minus 2 absolute value is less than 1, we know x plus 2 absolute value is less than 5. So x minus 2 times x plus 2 is less than x minus 2 absolute value times 5, which is less than epsilon. Now the quick check is finished. Let's continue. We divide the 5 to the other side, so now we have x minus 2 is less than 1 and x minus 2 is less than epsilon divided by 5. That's how close we want x to be to 2 so that x squared can be close to 4 to the level of epsilon. In other words, for any epsilon greater than 0, delta should be the smaller one between the two numbers 1 and epsilon divided by 5. A cleaner way of writing down the proof will be presenting our finding of delta without showing how we find it, and show that this delta does make absolute value of x minus 2 less than delta imply x squared minus 4 absolute value less than epsilon. In the next problem, we will present our proof in this way. Prove the limit of square root of x as x goes to 4 equals 2, which is to show for any epsilon greater than 0, there exists a delta greater than 0 such that absolute value of x minus 4 less than delta implies square root of x minus 2 absolute value less than epsilon. Now the proof goes like this. For any epsilon greater than 0, take delta to be a number that is both less than 1 and less than 3 epsilon. I didn't tell you how I found this delta. You might be able to see how this delta is found through the proof, but to prove something like this, we don't really need to show people how we find the delta. Now suppose the absolute value of x minus 4 is less than delta. Because delta is less than 1, so we know the distance between x and 4 is less than 1, so we know x is between 3 and 5. In particular, x is greater than 1. That is all we need for now. So assuming absolute value of x minus 4 is less than delta, we get x is greater than 1, which is a fact we are putting aside for later use. Now let's see if the distance between x and 4 is less than delta. What's the distance between square root of x and 2? We multiply the expression by square root of x plus 2 and divide it by square root of plus 2. Now the numerator is absolute value of x minus 4, which is the distance between x and 4, which is assumed to be less than delta. Now we will use the fact we got earlier, x is greater than 1, to make the denominator bigger, so the whole expression is smaller. And then we finish our estimate by remembering again the distance between x and 4 is less than delta, so the distance between square root of x and 2 is less than delta divided by 3. Remembering our choice of delta is also less than 3 epsilon, so delta over 3 is less than epsilon. So we have showed for any epsilon greater than 0, there exists a delta which can be any number less than 1 and 3 epsilon, such that the distance between x and 4 less than delta implies the distance between square root of x and 2 less than epsilon, which is the definition of saying the limit of square root of x as x goes to 4 is 2.